Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Cast iron is more than just metal. It is the backbone of modern civilization, hidden in plain sight. From the manhole covers under your feet to the massive engine blocks powering global shipping, iron is everywhere. But the journey from raw scrap to a precision-engineered component is a story of fire, chemistry, and extreme pressure. Today, we embark on a 15-minute journey inside the heart of the foundry to witness the complete transformation. Welcome to Simple Gyan. This is the science of molten metal at temperatures exceeding 1500 degrees Celsius. Our story begins over 2,000 years ago in ancient China, where the first cast iron was produced. It was the fuel of the Industrial Revolution, enabling the mass production of steam engines and railways. To understand the process, we must first look at the metallurgy. What makes cast iron different from steel? The secret lies in carbon content. While steel has less than 2%, cast iron contains 2 to 4%. In gray cast iron, this carbon forms flakes of graphite, which provide excellent vibration damping and machinability. By adding magnesium, we create ductile iron, where graphite forms nodules, making the metal strong and flexible. And then there is white cast iron, where carbon stays as iron carbide, creating a metal so hard it resists extreme wear. Chapter 2. The ingredients. A foundry's recipe begins with specific raw materials. Pig iron is the primary source, providing the base iron and carbon needed for the melt. Sustainability is key. Foundries recycle millions of tons of scrap steel and internal foundry returns. To fine-tune the properties, we add ferroalloys like silicon to control graphite formation and manganese for strength. Coke provides the heat in traditional furnaces, while limestone acts as a flux to pull out impurities. Chapter 3. The melting. This is where the solid metal is reborn as a liquid. The Cupola furnace is a vertical tower. It is continuous, meaning raw materials go in the top and iron comes out the bottom. A powerful air blast fuels the coke, creating temperatures high enough to melt tons of iron every hour. Modern plants prefer induction furnaces. Using electromagnetic fields, they melt iron with incredible precision and zero emissions. This method allows for rapid composition adjustments, making it the gold standard for high-performance ductile iron. For massive castings, some foundries use electric arc furnaces, capable of melting hundreds of tons in a single batch. Impurities float to the top as slag. This liquid waste must be skimmed off to ensure the final casting is clean and strong. Every batch is tested using an optical emission spectrometer. In seconds, we know the exact percentage of 20 different elements. Temperature control is critical. If the metal is too cold, it won't fill the mold. Too hot, and it will burn the sand. Chapter 4. The architecture of sand. Creating the mold is the most labor-intensive part of the foundry process. It starts with the pattern, a precise replica of the final part, oversized to account for metal shrinkage. Surface finish on the pattern determines the surface finish of the iron. Any imperfection here will be cast in metal. Green sand is the industry standard. It's a mixture of silica sand, bentonite clay, and just enough water to make it stick. This sand must be breathable to allow gases to escape during pouring, but strong enough to hold its shape. In high-volume foundries, automated vertical molding lines can produce hundreds of sand molds every hour. This automation allows for the mass production of the automotive parts we use every day. For massive castings like wind turbine hubs, foundries use resin sand, which uses chemical binders to create ultra-strong molds. These molds can weigh as much as a house and must withstand the immense pressure of tons of liquid iron. How do we create hollow spaces inside a solid casting? The answer is cores. Cores are made of high-strength sand and placed inside the mold cavity. The metal flows around them, leaving a void. After the iron solidifies, the core sand is shaken out, leaving behind a perfectly formed internal passage. The gating system is the plumbing of the mold. It must be designed to allow metal to flow smoothly without turbulence. Risers act as reservoirs of molten metal, feeding the casting as it shrinks to prevent internal holes or voids. Chapter 5. The River of Fire. This is the moment of truth where liquid meets form. Ladles must be preheated to prevent the metal from cooling down too quickly and to remove any moisture. Just before pouring, we inoculate the metal. This small addition of alloys triggers the right graphite structure. In smaller foundries, hand pouring is still common, requiring incredible coordination and physical strength. Large plants use automatic pouring systems. These machines use lasers to pour the exact weight of metal in seconds. Foundry workers wear aluminized suits. This fabric reflects the intense infrared radiation from the white-hot metal. As the metal enters, the moisture in the sand turns to steam. These gases must escape, or the mold will explode. It is a sensory experience. The roar of the furnace, the smell of burnt clay, and the intense heat on your skin. Chapter 6. The cooling. Once the mold is full, the physics of solidification take over. Iron solidifies by growing crystals called dendrites. The speed of this cooling determines the final strength of the part. Foundry engineers must manage cooling gradients. If one part of a casting cools too fast, it can create internal stress. As iron turns from liquid to solid, it shrinks. Without enough liquid metal from the risers, a pipe or hole can form inside. Some castings require heat treatment. By heating them back up to 900 degrees, we can soften the metal or improve its toughness. Chapter 7. The unveiling. This is where we separate the metal from the sand. The shakeout process uses massive vibration to break the sand mold, revealing the raw, dark gray iron casting inside. The gating system, the plumbing used for pouring, is now solid iron and must be removed and recycled. Shot blasting uses thousands of tiny steel beads to scrub the casting clean, removing every grain of burnt sand. Robotics has transformed the finishing room. Robots can grind with a precision and speed that no human can match. Chapter 8. Precision and quality. Every part must be perfect, because a single flaw can lead to catastrophic failure. Visual inspection is the first line of defense. Experienced eyes can spot defects that machines might miss. Ultrasonic testing looks inside the metal. High-frequency sound waves bounce off internal defects, alerting the team. For mission-critical parts like aerospace components, industrial X-rays provide a 3D view of the internal structure. Magnetic particle testing uses magnetic fields and fluorescent powder to make microscopic surface cracks visible. Finally, CMM machines verify that the part is accurate within microns of the original engineering blueprint. Chapter 9. The future. Foundries are no longer the dark, smoky places of the past. 3D sand printing allows us to create molds that were previously impossible to make in just a few hours. Digital twins and simulation software allow engineers to pour the metal virtually before ever melting a single pound. The industry is moving toward green foundries, focusing on 100% recycling and ultra-low emission melting. From raw scrap to precision casting, we have seen the incredible journey of cast iron. The next time you look at the world around you, remember the fire and science that built it. If you enjoyed this deep dive, please hit like and share. Your support helps us create more long-form industrial content. Thank you for watching. Subscribe to Simple Gaian and join our community of engineering enthusiasts. Bonus history. Did you know that the demand for cast iron cannons in the 1500s drove massive furnace innovations? Metallurgy fact. Adding just 0.05% magnesium is what turns brittle gray iron into strong, ductile iron. Safety fact. Every worker must stay hydrated. Foundries can reach ambient temperatures of 50 degrees Celsius. Sand fact. Foundries use subangular sand grains to allow air to flow through the mold, preventing gas pockets. Eco fact. Over 95% of all foundry sand is cleaned and reused, making it one of the most recycled industrial materials. Pouring fact. Bottom pour ladles ensure that only the purest iron at the bottom enters the mold, leaving slag behind. Pattern fact. Large foundries store patterns for decades, ready to cast a spare part for a 50-year-old machine. Automation fact. Driverless vehicles now transport molten metal, reducing human exposure to extreme heat zones. Testing fact. The wedge test is a traditional quick check to see how hard the iron will become before it is poured. Finishing fact. Vibratory finishing uses millions of tiny stones to polish iron parts to a smooth, automotive-grade finish. Ancient artisans used stack molding to cast hundreds of coins at once, showing early mastery of mass production. The Iron Bridge proved that cast iron could be used as a structural material, paving the way for the modern skyscraper. Inside the iron, atoms arrange themselves in layers. Perlite makes the metal strong, while ferrite makes it soft. Magnetic sorting ensures that only ferrous materials enter the charge, maintaining the chemical purity of the final melt. Furnace lining is the only thing protecting the steel shell from melting. This ceramic layer must be replaced every few weeks. If a core moves by even a millimeter, the entire casting is scrap. Precision seats called core prints hold them in place. Pouring too fast can cause thermal shock. The sand expands so rapidly that the mold wall can collapse or buckle. Engine engineers use finite element analysis to predict where stress will build up, adding cooling fins to the mold if needed. A typical shot blast cycle lasts 10 minutes, removing the burnt-on skin of sand to reveal the metallic luster beneath. Dye-penetrant testing is a simple yet effective way to find cracks that are too small to see with the naked eye. AI is now predicting defects before they happen, analyzing thousands of data points from the furnace to the mold. Gray iron is chosen for machine bases because its internal graphite flakes absorb vibrations, ensuring precision. Ductile iron is used for water pipes because it can bend without breaking, surviving earthquakes and ground shifts. In the mining industry, white iron is the only material hard enough to grind tons of rock without wearing away instantly. The induction coil is the heart of the modern foundry. It carries thousands of amps while being cooled by water inside. Core binders have evolved from simple oils to advanced resins that break down exactly when the metal solidifies. Casting yield is the measure of efficiency. Foundries aim to minimize the extra metal used in the gating system. Porosity is caused by trapped gas. If the sand isn't breathable enough, these bubbles get trapped in the solidifying iron. Surface finish requirements dictate the molding method. Shell molding uses fine sand to achieve a smoother, more accurate finish. Engine blocks are the ultimate test of casting. They require dozens of cores and perfect wall thickness for oil and water. Renewable energy relies on casting. These massive hubs must be defect-free to last for 25 years in the open ocean. Every time you hit the brakes, you rely on gray iron's thermal conductivity to move heat away from your wheels. Safety training has gone high-tech. New workers now use VR to experience the foundry floor before they ever step foot on it. Modern foundries are cleaner than ever. Advanced filtration systems capture 99.9% of all particulates before they leave. The foundry industry is a global network, connecting raw minerals to the machines that power our world. We've covered the chemistry of the melt, the technology of the furnace, and the architecture of the mold. And we've seen the precision of the pour, the power of finishing, and the strict standards of quality control. Our mission at Simple Gyan is to make the complex world of engineering accessible to everyone. Because behind every product is a process, and behind every process is the power of human ingenuity. Don't forget to subscribe and hit the bell icon to never miss a deep dive into industry and technology. I'm No Conbor E narrator G4SK2Ys. Thank you for watching this 15-minute journey. We'll see you in the next factory.